Okay, just for today's agenda so we know what we're doing, well, I'll just give you an update. Let's see, this is Wednesday, and a week from today, it's 12 o'clock. You can guess where you're going to be a week from today at 12 o'clock, right? Okay, I hope you'll be right here, because I'll be looking for you. You have my office hours for next week. They're on Blackboard website also if you need them. For the office hours before the exam, there's 4 office hours before your final. We'll talk more about that in about 40 minutes. But we want to do one last topic. I wasn't sure we had time to squeeze this in with our quarter system, with the holidays and exams, but we do have time today. So it's probably a good review problem too. How many people in here in 313 lab this quarter? Oh, wow, good, okay. You have run a test on a centrifugal pump. It depends on who your instructor was. You may have done some dimensional analysis with the pumps. But we're going to go through it today in with the textbook format. So here's where we start. This is a review also of dimensional analysis and similarity, so it's a good review for that. We start out and we say, all right, so we've got this centrifugal pump pumping fluid, maybe from one reservoir to a second reservoir. And I want to know what the power into the pump is a function of. And I'd say, well, probably the fluid we're pumping, so my guess might be density and viscosity. So I might put down here density and viscosity. Obviously, if I run the pump at a high pump speed, that's different than the power required to run it at a low speed. Okay, so omega is the speed of the pump. Omega is usually in radians per second. Capital omega sometimes is RPM, revolution, so the difference is 2 pi. We'll use omega. The pressure rise across the pump. The pump's purpose in life is to increase the pressure. The flow rate Q, sure, the more flow rate I put through the pump, the more I suspect the pump power has to be. And then another one is D. Now, D has nothing to do with the pipe diameter. It's the impeller diameter inside the pump casing. So this is the impeller diameter. Okay, so we'll do the dimensional analysis. We'll find out what we think are the important pipe parameters for this case. So we count them. Don't forget the guy on the left. He counts 1, 2, 3, 4, 5, 6, 7. Number of pies, 7. We can go ahead and list these guys. We've done it before. We won't do it again. You can list them. What rho is m over L cubed? What q is L cubed over t? What d is? It's a dimension, it's length, it's L. There's m, L, and t. What's omega? 1 over t. So there's 3, m, L, and t. So there's 4 important pi parameters, we think, 4. So what's the next step? All right, the next step, we'll just go through it like we did in the chapter on the pi theorem. We can choose 3 repeating variables. Let's go over the rules for that. Never choose the one on the left-hand side. He cannot be repeating. He should not be a repeating variable. Okay. Don't choose omega, q, and d. Okay. Length cubed per time, 1 over time. Do I see length at least once? Yes, yes. Do I see time at least once? Yes, yes. Do I see? Here it comes. Mass at least once? No, no, no. Okay. Don't choose omega dq as repeating. Anything else is legal and fair. So I chose repeating rho omega d. Okay, so let's go ahead and get one. So I'm going to say pi 1 is equal to rho to the a, omega to the b, d to the c. And then I'll go ahead and throw, let's throw mu over here. Okay. I go through here. I'm not going to go through all the gory details. You know what to do with that. You put this m over L cubed to the a and so on and so forth. Solve, set the coefficient of mass equal to a, the exponent of mass equal to 0, the exponent of time equal to 0, the exponent of length equal to 0. Solve for the a, b, and c. When you do that, you get rho omega d squared over mu. And then I let pi 2 equal rho to the a, omega to the b, d to the c. I don't use mu again now. I use another one I didn't. I can't use these three guys. No. And I used omega. No. And I used d. No. I just use mu. No. Okay, I'll use q now. Q. Play the same game, put the dimensions in there, write it in terms of mass to a power, time to a power, length to a power, and then set those equal to 0 and solve for the a, b, and c. And I'd get this, q over omega d cubed. Okay. Of course, you know, I told you, you're going to know if you made an algebraic mistake over here, because if that guy doesn't check out to be dimensionless, you made a mistake. So before you leave the problem on an exam, you always check the dimensions. Okay, so what you're saying, if you do this on an exam, you always want to check these dimensionless parameters to make sure they are dimensionless. That way you'll know if you're right or not. So, okay, we were checking this guy. L cubed over T for Q. Omega, radians per second. Radians is dimensionless. Don't use revolutions. Revolutions is not dimensionless. D cubed for this pump. This is the impeller diameter cubed. That's a length cubed. Cancel, 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 cancel. Yes, it's okay. All right. That's your check. You will always know if you made an algebraic mistake. Let's go on to our third one. We didn't use delta P yet. So pi 3 is equal to rho to the A, omega to the B, D to the C, times delta P. We go through the same situation we did before, and we find out that it's delta P over rho omega squared D squared. Check that guy. You'll see it's dimensionless. Okay. Then the last one, we put the left-hand side dependent variable, the power into the pump, W dot, pi 4. Rho to the A, omega to the B, D to the C, times the power into the pump. Notice we use the repeating variable in every pi parameter. Here they come. Rho omega D, rho omega D, rho omega D, rho omega D. That's what they're called repeating. Okay, we solve for this guy, solve for A, B, and C here, and we get this one. Okay, there they are. You can check those dimensions. You'll find out they really are dimensionless, so we're okay. And then when we're done, we can say that pi 4 is some function of pi 1 pi 2, pi 3. That's the way we write it. We put the pi parameter, which is a dependent variable, the w dot pi parameter, on the left. W dot parameter on the left. Other guys on the right as a function of. If you want to write it out this way, that's fine too. W dot over rho omega cubed d to the fifth equal some function of rho omega d squared divided by mu, comma, q over omega d cubed, comma, delta p over rho omega squared d squared. So there's the functional dependence in terms of dimensionless parameters for the power parameter. Now, sometimes they're given names. This guy here on the left, w dot over rho omega cubed d to the fifth, that's generally, we call that c sub w dot. That's the power coefficient. And then this one, q over omega d cubed. That's c sub q. We call that the flow coefficient. And then we have the delta p over rho omega squared d squared. We call that c delta p. And that's the pressure coefficient. And then the last one then down there is the, we've got the w dot, so we need our one right here. W dot rho, we got the rho delta p, we've got the q, we need this guy. So the rho omega d squared over mu. If I didn't want to use the pi theorem, let's say, you know what, the problem said solve for the important dimensionless parameters by using the pi theorem or any method you wish. Any method you wish, if you're given the choice. I might say, you know what, I see a Reynolds number right away. I'm not going to fool around. I see the Reynolds number. What's the Reynolds number? Rho v d over mu. Got it. What's the velocity in terms of length per time? Okay, I got that too. What if I take the velocity equal a length divided by time? A length, I need a length. I'm going to take d. And then I need a time. There, 1 over time. Meters per second, miles per hour, I don't care. D over t has the dimensions of a velocity. What's the Reynolds number? Rho times the velocity divided by mu. I'm going to replace that velocity. Don't forget, this is the impeller disk D. It's rotating at omega right there. There's a velocity on there, of course. There's a velocity on there. That's the velocity. So I replace the v with a d over t. That's my d over t, okay, omega. What do I have? Right there. There it is. Omega times d is like a velocity. So in my mind, I say, you know what? I got a velocity. It's omega times d. So there it is. I didn't have to use the pi theorem. Oh, I could. I get the same thing. But if I see it, then I see it. That's it. What is that thing right there? That's the Reynolds number. C times, this is called just the Reynolds number. I'd say, you know what? What's Q in? Q is L cubed divided by T. How can I get L cubed divided by T up here? Maybe if I take D, that's a length, and I cube it. D cubed, okay, yeah. And where's the time come from? Omega is 1 over time. Yep, I got it. There it is. I saw it in 15 seconds. I don't need to use the pi theorem because I see it right away. Oh, this guy here, he's tougher. He's tougher. This guy here, he's real tough to see it. Say, oh, I see that. It's very clear in my mind. I doubt it, but maybe you do. So sometimes you can use by observation. If you get stuck, you go to the pi theorem. Okay, it works most of the time. Okay, so there they are. These are all the coefficients. Okay, this guy's typically called Reynolds number, not C sub Reynolds number. But then we don't like to use him all the time. So pressure coefficient, we say here, recall that our, what is it, our delta P over gamma is equal to pressure head in the energy equation, the Bernoulli equation. That term in there is delta P over gamma. What's the units of that guy? Feet, pounds per square foot, pounds per cubic foot. What's the units? Feet. What's the head in? Feet or meters. Okay, put that guy over there. Delta P equal gamma H. So C sub H then, replace the guy with the head, G times H over omega squared D squared. Okay, so we're going to, he's called the head coefficient. That's the pump head, And you know what the pump head is, you know, here's Q. Here's a pump head. So there's the pump head graph. Centrifugal pump. Okay, so we have those important dimensionless parameters. And then we can take, now we had in the past, we've had graphs of pump head with different impeller diameters, and they look like this. These are different impeller diameters, D1, D2, etc. D3. Okay. This was the flow rate Q, typically. If we plot, this was at 1 RPM, if we plot that on C sub H on the y-axis, and we plot that with C sub Q on the x-axis. Why? Because I want the head. Where's the head? Right there, C sub H. I want the flow Q. Where's the flow? C sub Q. So I take the HP and Q graph and I plot it as a C sub H and C sub Q graph. And I get close. I can get close. I say, wow, that's really neat. Look at that. I plot all those points over there for those different diameters, and I end up with a graph that looks like that. All those points over there fall on close to a single curve on that graph. Well, that's the power of dimensionless numbers. So that's one way you can do the same thing. There are other curves. The C sub W dot curve looks like this. This is the C sub H curve. Okay. So you could take all the efficiencies from those different impeller diameters that the graph we had in class a while back, and plot those. They all fall on a single line. So you can plot the whole pump performance for different impeller diameters or different pump speeds on a single set of graphs. That's, of course, the power of dimensional analysis. It condenses a lot of material into a very simplistic format. Now, you're going to notice that the Reynolds number is not over there. Typically in a pump, the Reynolds number is not important, okay? Most of the time in a pump, the Reynolds number can be neglected and not considered. So we kind of eliminate him from the list as not being important because the impeller and the casing of the pump is typically rough. The flow is turbulent, but it's wild turbulent. It's not turbulent in a pipe. It's just turbulent flow. So it turns out that the Reynolds number is not important in a pump. So we don't show the Reynolds number over there. Okay. We show C sub H, C sub W dot, C sub Q, but we don't throw in the Reynolds number. It's not important in these kind of pump applications. Okay. Also in a pump, you can say it's turbulent flow, there's blade roughness, there's eddy formations, the spinning impeller creates eddies, there's flow separations in the pump, a ton of stuff going on in the pump. So we don't think the Reynolds number plays an important role in looking at pump analysis. Pipes, oh, for sure thing. Okay, so then the last thing is, pretty much this is dimensional analysis. This is how you present the results. What does this mean? It's a function of. I don't know the function until I plot the data. What's pi for? The W dot curve. Once I plot the experimental data, now you can see right there. Now I've got a curve. Now I can get a curve fit. I don't know what it is, second power, inverse, I don't know. But there's a function there. That's the function that this F represents right here. This is a function. Dimensional analysis won't tell us what the function is. Is it squared? Is it cubed? Natural log? Sinusoidal? That won't tell us. You've got to plot experimental data, and from the experimental data plot, now you can tell what the function might be. Okay, so all this is done. Stop. This is what the engineer wants. I want one graph that has for all different impeller diameters, all different pump speeds on this one graph. There it is. All right, so now let's go to your lab. The people that have had the lab, the people who are in the lab this quarter, they've probably done this. So we'll go through what you do in the lab. In the lab, you run a pump and pretty much you take water from a reservoir, you run it through the pump, it goes out, it goes through some flow meters, some valve systems, and it goes back into the reservoir. So pretty much that's what you've got. And let's say you run it at one speed. The speed I chose just kind of randomly let's see what I want to do here. I think I want to run it at 2900 first. So omega is 2900 RPM. Okay. And I get this data. Here's my data. I measure the flow rate Q1 by a turbine flow meter. This is in our lab, turbine flow meter. I measure the pump head by getting the pressure rise across the pump head. Okay, would that come from the energy equation across the pump? So I call this point 1, and I call this, I don't want to confuse that with that. I call this point A, and I call this point B. Okay. You measured the pressure rise across the pump. You measured the pump RPM. You measured the pump torque. All those things you measured in the lab. Okay. So you find the pump head by applying the energy equation across the pump from point A to point B. That gives you the pump head. So these are numbers here then, I'm just saying came from the data. 0, pump head 90. I don't know what the units are. You can call them meters, you can call them liters per second, whatever. You can call them GPM and you can call them feet. These are just numbers that are made up to show you what's going on. The flow rate, we'll just call it GPM for interest's sake, and this will be in feet. This is 90, still 90, 200, 88, 380, 365, getting to the maximum flow rate, 70. So when I plot that, it looks like this. I'll plot on the x-axis the flow rate. Q starts at 0. Let's go out to 400. 100, 200, 300, 400. And on the y-axis, we'll plot the pump head in feet. 20, 40, 60, 80, 100. That's the pump head in feet. Okay, so now I'm going to plot my pump data. You took this in the lab. 0 and 90 starts here. 190 right there. 288 right there. Boy, it's still really close right there. 300, it's 80. It's right there. 365, it's 70. 365 right here. Up to 70 right in the middle right there. There they are. Connect the black dots. Okay, there's the pump head at 2,900 RPM. Yeah. So that's what you did in the ME313 lab. And this is the beauty of dimensionless numbers and all that, is that somebody says, you know what, I made a mistake. I ran that pump at 2,900. I really meant to find out what the pump head was at 2,000 RPM. And so you tell them, okay, look, I'll run at 2,000, come back in 20 minutes, 30 minutes, I'll have it done for you. No, you don't have to run the pump test again. Once you've run it once at that speed, I can tell you what's going to happen at 2,000 RPM. So to find out what happens at 2,000 RPM, to get H sub P versus Q for 2,000 RPM, use similarity. Here's what similarity says. If this is similar, and of course it's the same pump, so it's similar. It's the same impeller diameter, so it's geometrically similar. What should I equate? The Reynolds number? No, I told you don't equate the Reynolds number. The power coefficient? No, I don't see power in that graph anywhere. The pump head? Oh yeah, there's HP. Got it. That's important. The flow parameter, Q over omega d cubed. Oh yeah, that's important. There's Q. So what do I equate? The important dimensionless parameters. What's the first one? Q. Equate the Q parameter. Okay, so Q, C sub Q for case 1 equals C sub Q for case 2. 1 means 2,900 RPM. 2 means 2,000 RPM. What is C sub Q? Okay, so now we put our C sub Q. It's Q over omega d cubed. And now I say, I'm not going to change the pump. It's the same pump. I'm just going to increase the speed. So did I change the impeller diameter? No, I didn't. I had the same pump. For the same pump, all I'm doing is changing the speed. The impeller diameter is in the casing. I'm not changing it. Cancel, cancel. Q2 is equal to omega 2 over omega 1 times Q1. Okay, there's my first important equation. What other parameter do I want to equate? Well, look at the graph over here. I equated the Q parameter, the flow parameter, flow coefficient. Now I'm going to equate the parameter that has the pump head in it. Okay, equate the pump head parameter. So next, CH of pump 1 equals CH of pump 2. The pump head parameter gives me this. H2 over H1. Okay, am I going to test the same pump at the same geographical location where the G's are the same? Yeah, the pump's in Pomona in our lab. I'm not going to move the pump to Denver and test it. In that case, G would change. No, I'm going to leave the pump in Pomona in the lab downstairs. So G's are the same. Cancel, cancel. Am I going to change the impeller diameter? No, it's the same pump. I'm just going to change the pump speed. Okay, the D's go out. Cancel, cancel. So H2 over H1 is omega 2 over omega 1 squared. I'll box that whole thing in. Okay, so now I'll put up here, H2 equal omega 2 over omega 1 squared times H1. There's the box. All right, here it comes. This side right here is for omega equal 2900 RPM. Okay, now I'm going to do the same thing for the pump. It's run at omega equal 2000 RPM. I'm not going to test the pump. I'm going to do it by similarity study. This is called Q2. This is called H2. So here's what I do. If I want to find Q2, I go over here, omega 2 divided by omega 1. I don't care what you use because this is the same thing as this. Because what's omega? Radians per second. Radians per second, they cancel out. What's this? Revolutions per second. Revolutions per second, they cancel out. I don't care if you use omega capital or omega small lowercase. Same thing, they cancel out. The units cancel out. Okay. Omega 2, 2000. Omega 1. This is omega 1. It's omega 2. Okay. Plug it in there. Well, if Q is 0, I get Q 0. Plug the other ones in there. I get 69. I get 138. I get 207. And I get 252. Now, I've chosen the same points over here, but I don't care what point you choose on this line. I don't care. Take 5 points on this line. Here's some other ones. Take this one, this one, this one, that one, and that one. Take some points that lie on that line. I don't care where they are on that line. Oh, the easy ones. I don't know. Maybe I'll take 100. Well, I did. There it is, okay? But you can take other points. Doesn't matter. They're not magical. Take any points on that line you drew and go through that table over there with these equations. Now I want H2. Okay, there, right there. There it is, H2. Omega 2, 2900, 2000. Omega 1, 2900. Square it times H1. Okay, here's H1. 90 times those RPMs squared. 42.8. 42.5, 41.9, 38.0, 33.3. Plot them. Okay, 0, 43. 0, 43 right here. I'm rhyming off here. 70, 43. 70, 43 right there. 138, 42. 140 and 42. 140 and 42. 207 and 38. 207 and 38 right there. 252 and 33, 252 and 30, 20, 33 right there. Where'd they come from? That table right there. What do you know? Connect the dots. Wow, I just did it. This is for 2,000 RPM. Did I actually test the pump at 2,000 RPM? No, I didn't. What did I do? I used the power of similarity studies to see what the pump would behave at if it was ran at 2,000 RPM. I can take any speed now. I don't care. 1,800, 1,700, as your lab took 1,700. You did 1,100. Doesn't matter. Once you run one pump test from experimentation, you can change the pump speed, or maybe you want to change the pump impeller diameter. Maybe you want to keep the pump speed the same, but change the impeller diameter. In that case, this becomes 1, and now it's the impeller diameter squared. In this case, this guy here is 1, but the diameters stay in there as the cubed. So you can also run this guy here and say, well, here's what would happen if I ran the impeller diameter at a different diameter, D2, and this would run at diameter D1, let's just say 15 centimeters, and this one was at 10 centimeters. So you can see how the pump would operate if you change the impeller. And most of these pumps, you can take the casing off the pump, take the impeller out of the pump physically, and put a new impeller in the pump, because there's different impeller diameters for one pump casing typically. So that's the power of dimensional analysis. You go through that stuff first, dimensional analysis, you find the important parameters, convince yourself that the Reynolds number is not going to play an important role, and then go over here with similarity studies, and then you can change things to where you can run a pump up here, and now without changing the impeller diameter, you can predict what that diameter would do. Without changing anything else, you can see what the speed would do, keep the diameter the same. All these curves come from similarity studies, and that's what you do in our fluid mechanics lab, ME313, with the pump. Okay, so a long story, but an interesting story. So we're going to stop there. And then that's going to be all we need to be concerned about them. Any questions on that before we stop? Okay, we're stopping there then. Yeah.